Welcome back to the third part of the series, which is Search and Artificial Intelligence. The algorithm we are going to learn about in this video is Breadth First Search, also known as BFS. In order to understand BFS, we need to know about a data structure called queue. Whenever an element is added in the queue, it is added to the rear of the queue, and also, an element can be deleted only from the front of the queue. In other words, a queue can be defined as a container open from both the sides, in which insertion and deletion takes place from different ends, the rear and the front of the queue respectively. When solving search problems using BFS algorithm, the frontier is a queue. The only main difference between DFS and BFS is that, in DFS we treat the frontier as a stack, while in BFS, we treat the frontier as a queue. Let's start by having node A and frontier in empty explored set. Frontier is not empty. Remove node A from the frontier. Node A does not contain the goal state. Add node A to the explored set. By expanding node A, we get node B as resulting node. Node B is not already in the frontier or the explored set. So add node B to the frontier. Frontier is not empty. Remove node B from the frontier. Node B does not contain the goal state. Add node B to the explored set. By expanding node B, we get node A, C and D as resulting nodes. Node A is already in the explored set while nodes C and D are not in the frontier or the explored set. So add only nodes C and D to the frontier. The order in which the resulting nodes will be added to the rear of the frontier is not fixed. So we could have added node D to the rear of frontier before node C. There is not a real preference here. Following any order, the only thing that matters in BFS is that, whichever resulting node gets added to the frontier, must be added to the rear of it. It is because the frontier is a queue, so we have to follow the rules. Frontier is not empty. As the frontier is a queue, so we will remove the node which is nearest to the front of the frontier, and that is node C. Node C does not contain the goal state. Add node C to the explored set. By expanding node C, we get node E as resulting node. Node E is not already in the frontier or the explored set. Considering that our frontier is a queue, we will add node E to the rear of the frontier. Frontier is not empty. Remove node B from the frontier. Node D does not contain the goal state. Add node D to the explored set. By expanding node D, we get node F as resulting node. Node F is not already in the frontier or the explored set. So add node F to the rear of the frontier. Frontier is not empty. Remove node E from the frontier. Node E contains the goal state, so return the solution. Solution is the sequence of actions we took which led us from node A to node E. The reason why this algorithm is called breadth first search is because it explores all the nodes of a graph in a breadthward motion. In other words, it explores all those nodes first which are closest to the node containing the initial state in terms of actions. It first explores the node which is 0 step away from the node containing the initial state, which is the node containing the initial state itself. Then it explores the nodes which are 1 step away from the node containing the initial state. Then it explores the nodes which are 2 steps away from the node containing the initial state. and so on. You get the idea? This process continues until the solution is found. In this graph example, we know that node A is the node containing the initial state. Node A is 0 step away from itself, so it gets explored first. Node B is 1 step away from node A, so it gets explored after node A. Node C and D are 2 steps away from node A, so they both get explored after node B. So in this way, solution is found. Now we will apply BFS technique to solve real-world problem like the maze problem, as we did in the previous part of this series with DFS. This is a maze in which only one solution exists. BFS will start exploration from the node which is marked I. At situations where BFS has to choose which node to explore first when multiple nodes are equal number of steps away from the node which is marked I, BFS will just randomly explore any one of the node first before the others. There is not a real preference here, as we discussed earlier. This process of exploring the nodes in a breadthward motion continues until the solution is found. We see that in problems where the node marked G is far away from the node marked I, or in other words, node marked G is lots of steps away from the node marked I. Then in these type of problems, BFS ends up exploring basically the entire graph. In comparison with DFS, DFS usually ends up leaving some unexplored nodes, as we saw in the previous part of this video series. Hence, in these kind of search problems, DFS performs much better than BFS. Let's use BFS to solve another maze problem in which 2 possible solutions exist. It's true that BFS had to explore some extra nodes which didn't lead us to the goal. But the solution BFS found us is indeed the optimal solution. Finding the optimal solution matters more than the number of nodes left unexplored. From the previous part of this series, we know that DFS does not guarantee optimal solution when multiple solutions exist. Whereas BFS guarantees optimal solution in only those problems where cost of all individual actions is the same, like the maze problem. Therefore, in problems where multiple solutions exist and cost of all individual actions is the same, BFS is much more suitable and effective than DFS. Let's take a look at an example which will make it clear why BFS can't find the optimal solution if cost of individual actions is not equal. If node A contains the initial state and state F contains the goal state, then 2 possible solutions exist. In the next video of this series, we will learn about another search algorithm, greedy best first search, also known as GBFS. GBFS is a lot different than DFS and BFS. Support me by subscribing my channel, liking, commenting, and sharing this video. Thank you.